Today, we're dissecting a problem that initially looks like a classic backtracking or power set generation task. But beneath the surface, there's a surprisingly elegant bitwise shortcut. Can you spot the optimization that turns an exponential solution into a linear one? The problem asks us to find the sum of all possible subset XOR totals for a given array of numbers. For each subset, we calculate the XOR sum of its elements. If a subset is empty, its XOR sum is 0. Our goal is to sum up all these individual XOR totals. This means generating all subsets, computing their XORs, and adding them together. A straightforward approach involves iterating through all possible subsets using a bit mask. For an array of size n, there are 2 to the power of n subsets. We can represent each subset with a mask from 0 to 2 to the power of n-1. For each mask, we iterate through the numbers, and if the corresponding bit in the mask is set, we include that number in the current subset's XOR sum. Finally, we add this XOR sum to our running total. This method works but generates each subset explicitly, leading to a time complexity of O of n times 2 to the power of n, and O of 1 space. The key insight lies in observing how each bit contributes to the final sum. Consider any specific bit position. If this bit is set in the overall bitwise OR of all numbers, it means at least one number in the input array has that bit set. Now, think about the subsets. For every subset where this bit is set in its XOR total, it contributes to the final sum. It turns out, due to the properties of XOR and subsets, if a bit is set in the overall bitwise OR of all numbers, it will be set in exactly half of all possible subset XOR totals. Since there are 2 to the power of n total subsets, half of them is 2 to the power of n-1. Therefore, the total sum is simply the bitwise OR of all numbers, multiplied by 2 to the power of n-1. Let's trace this with the example array, 1, 3. First, we calculate the bitwise OR of all numbers, 1 or 3. 1 in binary is 0, 1, 3 is 1, 1. 0, 1 or 1, 1 gives us 1, 1, which is 3. Now we need to multiply this result by 2 to the power of n-1. Here, n is 2 since there are 2 elements in the array, so n-1 is 1. 2 to the power of 1 is 2. Our final calculation is 3 multiplied by 2, which equals 6. This is our optimized result. Intuitively, each bit of the overall OR contributes its value times the number of times it appears in a subset XOR total. The half of subsets rule makes this calculation simple. For the input array containing 1 and 3, the sum of all subset XOR totals is 6. This is correct because the individual subset XORs are 0, 1, 3, and 2, which indeed sum up to 6. You'll spot this pattern when the problem involves summing values across all subsets, especially when the operation is XOR. The key signal is when the contribution of individual bits can be analyzed independently across the power set, rather than needing to construct each subset explicitly. Think bitwise properties over combinatorial enumeration. The optimal solution has a time complexity of O of n, because we iterate through the array once for the bitwise OR. The space complexity is O of 1, as we only use a few variables. This elegant bitwise trick is a powerful tool to add to your arsenal. Try the next problem involving subset sums to see if you can apply a similar pattern. Don't forget to like and subscribe for more concise DSA explainers.